Welcome back to Sleepy Scientist Stories, where tonight we become architects of infinity itself, weaving dreams from the very fabric of space-time. I'm here with you in this sacred space between waking and dreams, where the boundaries between imagination and reality blur like distant galaxies in the cosmic dawn. Whether you're nestled beneath starlit windows or wrapped in the warm embrace of midnight stillness, you've found your way to exactly where you need to be. Tonight, we're going to build a universe, not with our hands, but with our understanding, not with clay or light, but with the invisible threads of mathematics that weave through every atom, every star, every breath of space between the galaxies. And if this journey happens to be too fascinating, too beautiful to let you sleep just yet, well, there are far worse ways to spend the deep hours of night than learning how infinity unfolds from a handful of equations. Before we begin this cosmic meditation, take a moment to let your body settle into whatever surface holds you. Feel the weight of gravity, that same force we'll soon watch sculpt entire galaxies, gently pulling you toward rest. Let your breathing slow to match the ancient rhythm of stellar formation, where each breath takes 1,000,000 years, and each heartbeat spans the birth and death of suns. If you find wonder in these cosmic lullabies, I invite you to share that wonder. Let others know that here, in this digital campfire of consciousness, minds from around the world gather to dream the same dreams at slightly different hours. Tell me in the comments, where are you listening from? What time cradles you right now? There's something profoundly beautiful about knowing that as you drift towards sleep in New York, someone in Tokyo is awakening to the same stars, the same infinite questions. Now, close your eyes if you can. Let your imagination become a canvas not of sight, but of pure possibility. Picture, if you will, a darkness so complete it makes midnight seem bright. Not the absence of light, but the presence of potential, infinite, patient, waiting. This is where every universe begins, in the mind of a scientist who dares to ask, what if? In the beginning, there is only code, lines of text that seem unremarkable, sitting quietly in computer memory like seeds waiting for spring. But these are no ordinary seeds. These are the compressed dreams of physicists, the mathematical DNA of reality itself, written in languages that speak directly to the silicon hearts of machines. A scientific simulation is not a movie. It's not entertainment dressed up as education. It's something far more profound. It's a prayer written in mathematics, a hymn composed of differential equations, a love letter to the universe asking it to reveal its deepest secrets. Let this resonate, speaking more slowly. When scientists create these digital cosmos, they're not trying to fool anyone into believing pixels are planets. They're doing something far more elegant. They're teaching machines to dream in the language of physics. Every simulated galaxy, every swirling nebula, every collision between cosmic titans, all of it emerges from the same fundamental equations that govern the real universe spinning silently around us right now. Think of it as teaching a computer to paint with gravity instead of light, to sculpt with time instead of clay. The canvas is vast, sometimes larger than our observable universe. The paint is pure mathematics. And the artist? The artist is our collective human curiosity, channeled through lines of code that can run for weeks on supercomputers, slowly bringing entire cosmic histories to life, building emotional connection. There's something almost mystical about watching a simulation unfold. In the beginning, you see only dots scattered across empty space, millions, sometimes billions of them, each representing vast clouds of matter larger than entire solar systems. They appear random, chaotic, meaningless. But then, time begins to flow, and with each passing 1,000,000 years, compressed into seconds of computation, those dots begin to dance. Slowly, so slowly you might miss it if you're not watching carefully, patterns emerge from the chaos. Matter calls to matter across the void. Gravity, patient and inexorable, begins its eternal work of bringing things together. Paint the visual with words. Filaments stretch across the darkness like the neural pathways of some cosmic mind. Nodes of light appear where multiple streams converge, growing brighter and more complex with each passing eon. Voids, vast empty chambers larger than anything the human mind can truly comprehend, open up between the growing structures, and suddenly you're not looking at a computer screen anymore. You're looking at the universe being born. Picture, if you will, a darkness so complete it makes midnight seem bright. Not the absence of light, but the presence of potential, infinite, patient, waiting. This is where every universe begins, in the mind of a scientist who dares to ask, what if? In the beginning, there is only code, lines of text that seem unremarkable, sitting quietly in computer memory like seeds waiting for spring. But these are no ordinary seeds. These are the compressed dreams of physicists, the mathematical DNA of reality itself, written in languages that speak directly to the silicon hearts of machines. A scientific simulation is not a movie. It's not entertainment dressed up as education. It's something far more profound. It's a prayer written in mathematics, a hymn composed of differential equations, a love letter to the universe asking it to reveal its deepest secrets. When scientists create these digital cosmos, they're not trying to fool anyone into believing pixels are planets. They're doing something far more elegant. They're teaching machines to dream in the language of physics. Every simulated galaxy, every swirling nebula, every collision between cosmic titans, all of it emerges from the same fundamental equations that govern the real universe, spinning silently around us right now. Think of it as teaching a computer to paint with gravity instead of light, to sculpt with time instead of clay. The canvas is vast, sometimes larger than our observable universe. The paint is pure mathematics. And the artist is our collective human curiosity, channeled through lines of code that can run for weeks on supercomputers, slowly bringing entire cosmic histories to life. There's something almost mystical about watching a simulation unfold. In the beginning, you see only dots scattered across empty space, millions, sometimes billions of them, each representing vast clouds of matter larger than entire solar systems. They appear random, chaotic, meaningless. But then, time begins to flow, and with each passing million years, compressed into seconds of computation, those dots begin to dance. Slowly, so slowly you might miss it. If you're not watching carefully, patterns emerge from the chaos. Matter calls to matter across the void. Gravity, patient and inexorable, begins its eternal work of bringing things together. Filaments stretch across the darkness like the neural pathways of some cosmic mind. Nodes of light appear where multiple streams converge, growing brighter and more complex with each passing eon. Voids, vast empty chambers larger than anything the human mind can truly comprehend, open up between the growing structures. And suddenly, you're not looking at a computer screen anymore. You're looking at the universe being born. But how does one teach a machine to dream of galaxies? How do you compress the infinite complexity of the cosmos into something a computer can understand? It begins with a kind of beautiful simplification. Every particle in a cosmic simulation, and there might be billions of them, doesn't represent a single atom. Instead, each one stands for something unimaginably vast, a chunk of matter that might contain entire solar systems condensed into a single point of mathematical light. These particles are like actors in a play where each performer represents thousands. One particle might embody a dwarf galaxy. Another might stand in for a nebula so large that light takes centuries to cross it. They don't look like anything. They're just numbers in a computer's memory. But, oh, what stories these numbers tell. Each particle carries within it a universe of information. Its position in three-dimensional space, recorded to extraordinary precision. Its velocity, how fast it's moving, and in which direction through the cosmic void. Sometimes its temperature, glowing hot from ancient collisions or cooling in the darkness between stars. Even its chemical composition, the recipe of elements forged in stellar furnaces billions of years ago. But particles alone are just ingredients scattered across an infinite kitchen. They need forces to bring them together, to cook them into something magnificent. And in the cosmic kitchen, there are master chefs whose names we know by heart: gravity, electromagnetism, and the fundamental forces that shape reality itself. Gravity is the great sculptor of the universe, patient, inexorable, working across distances so vast that light itself grows tired traveling between its influences. In our simulations, gravity follows the same elegant mathematics that Newton glimpsed centuries ago, every particle attracted to every other particle with a force that depends on their masses and the square of the distance between them. It sounds simple, doesn't it? Almost quaint. But when you have billions of particles, each pulling on billions of others, the mathematics becomes a symphony of such complexity that only the most powerful computers can hope to conduct it. Each particle must feel the gravitational whisper of every other particle, no matter how distant, no matter how faint that whisper might be. To make this computationally possible, scientists have developed elegant shortcuts. Instead of calculating every interaction individually, a task that would take longer than the age of the universe itself, they group distant particles together, treating faraway galaxy clusters as single, massive objects. It's like looking at a forest from a great distance. You don't need to see every leaf to understand the shape of the canopy. But gravity, magnificent as it is, cannot work alone. In the spaces between the great gravitational architectures, other forces hold sway. Electromagnetism governs the behavior of gas and plasma, those tenuous clouds of matter that glow and flow and eventually condense into stars. Hot gas radiates its energy into the cosmic dark, cooling and contracting until gravity can finally claim it. These electromagnetic forces are what make simulations truly come alive. They allow gas to flow like cosmic rivers, to compress into dense knots where stars are born, to expand in great bubbles blown by stellar winds and supernovae. They create the turbulence and complexity that transforms simple gravitational collapse into the rich, chaotic beauty of galaxy formation. And then there is the mystery that haunts every simulation: dark matter, invisible, untouchable, yet comprising most of the mass in every galaxy, every cluster, every large-scale structure in the universe. In our digital cosmos, dark matter particles move like ghosts through the ordinary matter, feeling only gravity's pull, immune to light and heat and electromagnetic force. These dark matter particles form the invisible scaffolding upon which the visible universe is built. They collapse first, creating gravitational wells that later trap and compress ordinary matter. Without dark matter, our simulations produce universes that look nothing like our own, galaxies that form too late or not at all, structures that are too small or too large, a cosmos that fails to match the intricate web of light and shadow we see through our telescopes. The mathematics that governs all of this is written in the language of differential equations, formulas that describe how things change over time. They tell us how particles move in response to forces, how gas flows and compresses, how energy radiates away into the cosmic background. These equations are often nonlinear, meaning small changes can lead to dramatically different outcomes, like butterflies, whose wings can influence the formation of hurricanes, or in this case, the birth of galaxies. To solve these equations, time itself must be broken into tiny fragments. The computer steps forward through cosmic history in increments of thousands or millions of years, calculating at each moment how every particle should move, how every force should act. The choice of time step is crucial. Too large, and the simulation becomes unstable, reality breaking down into mathematical chaos. Too small, and the calculation would take forever, cosmic histories stretching longer than the real cosmic history they're trying to simulate. Beneath all of this mathematical machinery lie the fundamental constants of nature, numbers so precisely tuned that tiny changes would render our universe unrecognizable. The strength of gravity, the speed of light, the mass of the proton, the fine structure constant that governs electromagnetic interactions. These numbers are woven into every calculation, the cosmic constants that set the tempo and rhythm of universal evolution. But even with all this computational power and mathematical sophistication, simulations must make compromises. Some processes are too complex, too chaotic, too dependent on microscopic details to model directly. the way individual stars form within collapsing gas clouds, the precise feedback from supernovae and stellar winds, the intricate dance of magnetic fields in galactic disks. These require what scientists call subgrid models, simplified rules that approximate the average behavior of processes too complex to simulate in full detail. These subgrid models are where the art of simulation reveals itself. They must be carefully calibrated against observations of real galaxies, real star formation, real cosmic processes. Too little feedback from stellar formation and simulated galaxies grow too massive, consuming all their gas in a frenzy of starbirth. Too much feedback and galaxy formation shuts down entirely, leaving a universe filled with dark matter halos, but no stars, no light, no complexity. It's a delicate balance, this dance between the known and the unknown, between the processes we understand and those we must approximate. Every simulation is an hypothesis about how the universe works, a mathematical model that can be tested against the real cosmos. When simulations fail to match observations, when they produce galaxies that are too red or too blue, too massive or too sparse, distributed in patterns that don't match what telescopes reveal, they point toward gaps in our understanding, mysteries yet to be solved. And yet, despite all these approximations and simplifications, something magical happens when you set these digital universes in motion. From the cold mathematics of differential equations and particle interactions, structures emerge that look startlingly, breathtakingly similar to the real universe around us. Cosmic webs stretch across simulated space, their filaments glowing with the light of newborn galaxies. Great clusters form where multiple filaments intersect, their gravitational fields so strong they bend light itself. Voids open up between the structures, vast empty regions where matter is so sparse that entire volumes the size of our local galaxy group contain almost nothing at all. Individual galaxies develop personalities within these simulations. Some grow into great spiral disks, their arms marked by waves of star formation that spiral outward like cosmic hurricanes. Others become elliptical giants, their stars scattered in smooth, featureless distributions. Still others remain small and irregular, their formation interrupted by the gravitational harassment of larger neighbors. These digital galaxies collide and merge, their dark matter halos interpenetrating like ghosts, while their stellar populations are scattered and mixed. Gas clouds slam together at tremendous speeds, shocking and heating until they glow with the light of 1 billion suns. Black holes, those ultimate gravitational monsters, grow at the centers of the largest galaxies, feeding on infalling matter and occasionally blazing forth as quasars that outshine entire galaxy clusters. Time flows differently in these simulated universes. Billions of years pass in hours of computation. The formation and evolution of structures that took the real universe most of its 13.8 billion year history to create can be watched unfolding on computer screens in fast forward, like watching flowers bloom in time-lapse photography, except these flowers are galaxies, and the garden is the entire observable cosmos. And perhaps most remarkably of all, these simulations can be rewound and replayed, with different initial conditions, different assumptions about dark matter, or dark energy, or the processes of star formation. They become time machines that let us explore the paths not taken, the universes that might have been if the cosmic dice had fallen differently in the first moments after the Big Bang. Some simulations explore what would happen if dark energy were stronger or weaker, if the universe expanded faster or slower. Others investigate alternative theories of gravity, different models of dark matter, variations in the properties of ordinary matter itself. Each run is an experiment in cosmic evolution, a test of our theories against the ultimate laboratory, an entire simulated universe. The results of these experiments often surprise their creators. Complex behaviors emerge that no one anticipated, patterns and structures that arise naturally from the interplay of simple physical laws. Galaxies develop in ways that theorists hadn't predicted. Cosmic structures form networks and hierarchies that reveal new principles of organization. The universe, even in simulation, remains full of surprises. This is the profound gift that simulations offer to cosmology. They transform abstract mathematical theories into visual, tangible experience. They let us see the invisible forces that shape the cosmos, Watch the slow dance of gravity across billions of years. Witness the birth and death of galaxies in the safety of computer memory. But perhaps most importantly, they remind us that the universe is not a static thing, frozen in time like a photograph. It's a dynamic, evolving, ever-changing tapestry of matter and energy, constantly transforming itself according to laws so fundamental and beautiful that they can be captured in mathematics and brought to life in code. Every simulation is both a mirror of the universe and a product of human curiosity. It reflects our current understanding while revealing the boundaries of our knowledge. It shows us not just what the cosmos is, but what we think we know about what it is. And sometimes, gloriously, it shows us that we were wrong, that the universe is stranger and more wonderful than our theories had dared to suggest. As you drift towards sleep tonight, carried by these images of digital cosmos and simulated stars, remember that the real universe around you is no less magnificent than these computer-generated dreams. The same forces that shape galaxies in simulation are at work right now, pulling on every atom in your body, connecting you to the cosmic web that stretches from here to the edge of the observable universe. You are not separate from the cosmos. You are part of it, made of elements forged in stellar cores, shaped by the same gravity that builds galaxies, participating in the same cosmic story that our simulations are trying so desperately to understand. And in that recognition, in that moment of cosmic connection, perhaps we find the deepest purpose of these digital universes. Not just to understand the cosmos, but to understand our place within it, to see ourselves not as observers standing outside of nature, but as conscious participants in the greatest story ever told, the story of how the universe came to know itself through beings like us, who can dream of distant galaxies and bring them to life in silicon and code. Sleep well, cosmic dreamer. The real universe will still be here when you wake, just as mysterious and magnificent as the simulations that help us glimpse its secrets. And who knows, perhaps in your dreams tonight, you'll find yourself floating through digital cosmos of your own making, watching galaxies form and stars be born in the infinite laboratory of imagination. The universe is vast, and we are small, but we are not insignificant. We are the way the cosmos has learned to think about itself, to wonder at its own beauty, to ask the questions that drive us to build digital universes in search of answers. And that, perhaps, is the most remarkable simulation of all. In the beginning, there was darkness, not the darkness of space, but the darkness of unknowing. Scientists gazed up at the star-scattered sky, wondering how the universe came to be so beautifully, mysteriously structured. Galaxies spiraled like cosmic pinwheels, connected by invisible threads of light, separated by vast oceans of emptiness. How did such complexity emerge from the simple, smooth beginning described by the Big Bang? The answer would come not from telescopes alone, but from something far more unexpected, from machines that could dream. Imagine, if you will, the first cosmological simulations of the 1970s. Picture primitive computers, their screens glowing amber in darkened laboratories. On these screens, just a few dozen points of light dance slowly across the display, each one representing not a star, but an entire galaxy. These early digital universes were humble things, barely more complex than a child's mobile spinning above a crib. Yet in their simple movements lay the seeds of revelation. The scientists watched, transfixed, as gravity worked its patient magic. The points began to cluster, drawn together by invisible forces. Some grouped into pairs, others formed larger gatherings, and slowly, beautifully, a pattern emerged. It was delicate and intricate, like frost forming on a winter window. Clusters of matter connected by thin, thread-like filaments, with vast, empty spaces stretching between them. The universe wasn't just expanding randomly, it was sculpting itself into something magnificent. But these early simulations felt incomplete, like a symphony missing its deepest notes. Something profound was absent from their digital cosmos. The galaxies in these early models moved too slowly, clustered too weakly. The real universe seemed to pulse with hidden energy, held together by forces that remained invisible to human eyes. Then came the revelation that would change everything, dark matter. Picture this mysterious substance, not dark because it's black, but dark because it refuses to reveal itself to light. It neither glows nor absorbs the photons that paint our visible universe. Yet it tugs on everything with its gravitational embrace, like a cosmic puppeteer pulling strings we cannot see. When scientists began weaving dark matter into their digital tapestries, everything transformed. The simulations awakened with new life, new complexity, new beauty. Dark matter moves through space like a cosmic ghost, interacting only through gravity's gentle touch. In the simulations, it forms vast, spherical halos, invisible shells where dark matter grows dense and patient. And within these phantom cradles, galaxies are born, like pearls nestled in shells made of shadow. This discovery gave the simulations their backbone, their hidden architecture upon which all visible beauty could rest. As computing power blossomed through the 1990s, these digital universes grew ever more magnificent. Scientists could now simulate millions, then billions of particles, each one a tiny actor in a cosmic drama spanning eons. The results were breathtaking. Massive filaments of dark matter stretched across their screens like cosmic highways, connecting galaxy clusters in an infinite web. Shockwaves rippled through gas clouds like pebbles dropped in a celestial pond. The large-scale structure of the universe began to mirror what astronomers saw through their telescopes, not just a theoretical model, but a genuine reflection of reality. But perhaps the most beautiful evolution came when scientists began anchoring their simulations to real observations. They used the cosmic microwave background, that faint, ancient glow left over from the Big Bang, to set the initial conditions of their digital worlds. These tiny temperature variations became the seeds from which galaxies and clusters would grow over billions of years. It was as if the simulation was being handed a baby photograph of the universe and asked to predict what that infant cosmos would look like 13 billion years later. The phrase "universe in a box" became the poetry that described these efforts. Each simulation defined a volume of space, perhaps a cube 100 million light-years across, and populated it with virtual matter. Then, like watching time-lapse photography of a flower blooming, the simulation would evolve this cube over billions of years, step by careful step, according to the laws of physics. Each particle's journey would be calculated, each interaction recorded, each gravitational whisper noted and remembered. These boxed universes revealed wonders beyond imagination. They showed how dark matter halos merged like cosmic dancers, how galaxies fell into clusters like leaves gathering in autumn streams, and how cosmic voids formed between dense regions like bubbles in champagne. They demonstrated the elegant power of gravitational collapse and helped confirm that cold dark matter was indeed the universe's hidden sculptor. Most remarkably, these simulations became laboratories where impossible experiments could unfold. In the real universe, you cannot rewind time or adjust fundamental constants. You cannot change the amount of dark matter or tweak the expansion rate to see what happens. But in a simulation, you can. You can play Cosmic God, adjusting parameters like an artist mixing colors on a palette, then pressing play to watch your synthetic universe unfold in new and beautiful ways. The early limitations were real: low resolution, simplified physics, heavy reliance on assumptions. But the foundation had been laid with mathematical precision and poetic grace. Scientists had learned that gravity could sculpt complexity from simplicity, that digital tools could reveal patterns too vast, too slow, or too distant to observe directly. What started as mere dots on primitive screens had become something far more powerful, a new way of seeing not just the universe as it is, but the universe as it might have been, or might still become. In the early 2000s, a team of visionary scientists decided to build something wildly ambitious, a digital universe so vast, so detailed, and so thoroughly rooted in modern physics that it would stretch supercomputers to their breaking point. This wasn't science fiction or academic daydreaming. This was real, and it would become one of the most influential simulations in the history of cosmology. Its name whispered reverence: the Millennium Simulation. The Millennium Simulation aimed to capture nothing less than the entire visible universe, not in perfect clarity, but in astonishing detail for its time. Launched in 2005 by the Max Planck Institute in Germany, this digital masterpiece modeled the evolution of cosmic structure from about 400,000 years after the Big Bang all the way to the present day. That's over 13 billion years of expansion, collapse, clumping and reshaping, all compressed into a sprawling numerical ballet that danced across computer screens like Aurora Borealis made of mathematics. To achieve this cosmic symphony, the scientists employed 10 billion particles. Not real particles, of course, but computational ones, each representing a massive amount of dark matter. Together, they mapped out a chunk of the universe 2 billion light-years across. Let that sink into your consciousness, like a stone dropped into a still pond. 2 billion light-years. That's about 1/15 the size of the observable universe, a cube of space so large it encompasses tens of millions of galaxies, all their motions governed by gravity's patient, inexorable pull. Imagine trying to simulate the weather for an entire planet, not just for a week, but for billions of years. The Millennium simulation accomplished exactly that cosmic feat. But what made it truly special wasn't just its scale, it was the precision, the ambition, and the quietly profound philosophical implications of what it represented. For the first time, scientists could study the cosmic web not as a theoretical construct or a distant telescope image, but as a living, breathing, evolving structure they could examine from every angle. To run a simulation of this magnitude required serious computational muscle. The Millennium simulation executed on a supercomputer that crunched through gravity's equations for months, updating the position and velocity of every particle again and again as cosmic time ticked forward in small, calculated steps. The output wasn't initially a pretty picture, it was raw data, petabytes of floating point numbers describing where each particle existed at each moment in time. But when this data was processed and visualized, it revealed something extraordinary. A digital version of the large-scale universe that looked hauntingly familiar. Filaments and clusters sprang into view like constellations appearing at twilight. Cosmic voids stretched across the simulated sky like vast, empty cathedrals. It was as if someone had taken a slice of reality, turned it inside out, rebuilt it from first principles, and let it unfold according to the universe's deepest laws. The Millennium simulation focused solely on dark matter, which makes up the bulk of the universe's mass and dominates cosmic structure formation. Ordinary matter, gas, stars, galaxies, was added later using semi-analytic models, mathematical recipes that decorated the dark matter framework with educated guesses about how galaxies might form, evolve, and die. It was like baking a cake using only the essential ingredients, then decorating it afterward with frosting and sprinkles based on careful observation and theory. The importance of this simulation ripples through cosmology, like waves from a dropped stone. It allowed scientists to run virtual surveys of the universe, to pretend to be astronomers inside the simulation, pointing virtual telescopes in any direction to see what structures would appear. These mock observations could be compared to real data, helping identify inconsistencies and gaps in understanding. If a real telescope showed more galaxies than the simulation predicted, it raised flags. Was something missing from the physics? Or was the telescope detecting something unexpected? The simulation also helped settle cosmic debates. There was ongoing tension between warm dark matter and cold dark matter models. Warm dark matter particles move faster, erasing small-scale structure like an eraser smoothing pencil marks. Cold dark matter moves slowly, allowing finer, more delicate clumping. The Millennium simulation strongly favored cold dark matter, showing it naturally produced the kind of cosmic web astronomers actually observe through their telescopes. The word Millennium wasn't just a fancy title, it reflected the scope of the project, spanning cosmic time, illuminating billions of years of evolution, establishing a new benchmark for what was possible. Other researchers began designing follow-up simulations with even more particles, more sophisticated physics, better resolution. But the Millennium simulation remained the standard-bearer, the golden reference point against which all others were measured. Yet it also raised profound questions that drift through the mind like distant music. If we can simulate the large-scale universe with such startling accuracy, what does this say about our understanding of the cosmos? The simulation worked because it made certain assumptions about dark matter's nature and the universe's initial conditions, assumptions based on the best available data, but still fundamentally educated guesses. Beautiful, complex, extraordinarily informed guesses that happen to work remarkably well. The Millennium simulation also had limitations that kept it humble. It possessed incredible breadth but relatively coarse resolution. Each particle represented a massive chunk of dark matter, millions of times more massive than our Sun. Smaller structures like individual galaxies were effectively smoothed over, requiring different simulations that traded cosmic volume for exquisite detail. But the visualization produced from Millennium data achieved something rare in theoretical physics. They were genuinely beautiful. Vast webs of light traced invisible structure like frost patterns on cosmic window panes. They didn't just inform, they inspired. Students, scientists, and stargazers could look at these images and feel, in some deep and quiet way, that they were seeing the very bones of reality laid bare. Some joked that the simulation was so detailed we might as well be living inside it, a tongue-in-cheek reference that hints at something quietly profound. If a simulated universe can match our own in structure and behavior, how do we define what's real? The simulation doesn't answer this philosophical riddle, but it makes the question harder to ignore, like a melody that lingers long after the music stops. If the Millennium simulation was a grand sketch of the cosmos, then Illustris became digital astronomy's Renaissance masterpiece. Launched in 2014 by an international team of astrophysicists, Illustris took the idea of building a universe and brought it into high definition. It didn't just track dark matter's invisible scaffolding, it modeled how gas flows like cosmic rivers, how stars ignite like celestial candles, how black holes feed like hungry cosmic mouths, and how galaxies evolve like living organisms across billions of years. The visual beauty that emerged made even hardened scientists stop and stare in wonder. Where earlier simulations focused primarily on dark matter and used basic approximations for visible structures, Illustris sought to show not just where galaxies form, but how they grow, interact, merge, and scatter their starlight across the cosmic dark. The result wasn't just more accurate, it was astonishingly lifelike, like watching the universe's own home movies. Spiral galaxies swirled with graceful arms reaching into darkness. Massive elliptical galaxies glowed with the accumulated fire of ancient stellar collisions. Intergalactic gas streamed and swirled like aurora caught in cosmic tides, painting the space between galaxies with invisible beauty. The numbers behind this artistry were equally impressive. Illustris simulated a cube of space about 350 million light-years across, using over 12 billion resolution elements. Particles and fluid cells representing gas, dark matter, stars, and black holes. Each element carried its own properties like a cosmic passport: mass, velocity, temperature, chemical composition. As the simulation ran, these properties evolved in response to physics equations governing gravity, hydrodynamics, star formation, radiation, and more. It was like watching a digital universe breathe, stretch, and swirl as it expanded through time, every motion choreographed by the fundamental forces of nature. At Illustris's heart lay a clever algorithm called Arapo, a computational technique that used a moving mesh instead of fixed grid boxes. This flexible grid adapted to matter's flow like a cosmic net that could reshape itself, allowing the simulation to maintain both high accuracy and computational efficiency, even in regions with complex dynamics like star-forming galaxies or turbulent gas clouds. What truly set Illustris apart wasn't just its visual fidelity, but its ambitious scope. The team ran multiple simulations at different resolutions, carefully balancing size and detail like an artist choosing between broad brushstrokes and fine details. They included feedback processes from stars and supermassive black holes, cosmic phenomena that play crucial roles in shaping galaxies across cosmic time. When massive stars explode as supernova, they blast energy into their surroundings like cosmic fireworks, stirring gas and slowing further star formation. Black holes operate on grander scales, spewing jets of hot gas that can push material out of galaxies altogether, like cosmic winds reshaping the landscape of space itself. These feedback mechanisms are notoriously tricky to model because they occur on small scales but create effects that ripple across cosmic distances. As you approach a black hole, the gravitational field becomes so intense that space itself is dragged along like honey, and time slows to a crawl compared to distant observers. Imagine descending toward Sagittarius, a star, the supermassive black hole at the center of our galaxy, with a mass 4 million times greater than our Sun. As you fall inward, initially the time dilation effects would be subtle, similar to what we observe near massive stars. But as you approach the event horizon, the point of no return beyond which even light cannot escape, time dilation accelerates dramatically. At just twice the distance from the event horizon, time would run at about 70% the rate experienced by distant observers. Closer still, at 10% beyond the event horizon distance, time would crawl at less than half its distant rate. But the truly mind-bending effects occur in those final moments of approach. At the event horizon itself, time dilation becomes infinite from the perspective of distant observers. This creates one of the most haunting predictions of general relativity. If you were watching someone fall into a black hole, you would never actually see them cross the event horizon. Instead, you would observe them slowing down, their movements becoming more and more sluggish as they approached the point of no return, their image growing redder and dimmer until it faded from view. From your perspective, they would appear frozen in time at the event horizon for eternity. Yet from the falling person's perspective, something entirely different would occur. They would cross the event horizon in a finite amount of their own time, experiencing nothing particularly special at that moment. The extreme time dilation that stretches their final approach into infinity from an outside perspective is invisible to them. They continue to experience time normally, even as the outside universe ages eons in what feels like moments to them. This is the paradox of black hole time dilation, two equally valid perspectives on the same event that seem to contradict each other completely. The mathematics behind these effects reveal the true power of black holes as time machines. The closer you orbit to a black hole without falling in, the more extreme the time dilation becomes. There exists a theoretical orbit at 1.5 times the black hole's Schwarzschild radius, called the photon sphere, where light itself can orbit the black hole. At this distance, time dilation is so extreme that enormous amounts of time would pass in the distant universe, while you experience relatively brief periods. A journey of a few hours in this region could correspond to years, decades, or even centuries passing elsewhere in the universe. Consider the dramatic scenario depicted in science fiction, but grounded in real physics. An astronaut who ventures close to a massive black hole and then returns to Earth. The time dilation effects could be so extreme that they return to find centuries or millennia have passed. On Earth, while they experienced only days or months, they would have literally travelled into Earth's future, not through any exotic technology, but simply by exploiting the warping of space-time near a black hole's tremendous mass. The largest black holes in the universe make the most efficient time machines. Supermassive black holes, like those found at the centres of galaxies, can contain billions of times the mass of our Sun. Near these giants, the event horizon is so large that the tidal forces, the difference in gravitational pull between your head and feet, wouldn't immediately tear you apart. You could theoretically survive much closer to the event horizon, experiencing even more extreme time dilation effects. For such massive black holes orbiting just outside the event horizon could allow you to experience hours while years or decades pass in the outside universe. The rotating black holes, called Kerr black holes, add yet another layer of temporal complexity. These spinning giants drag space-time around with them in a phenomenon called frame dragging, or the lens-thirring effect. Near a rapidly rotating black hole, space itself is pulled along in the direction of rotation, creating regions where remaining stationary relative to distant stars becomes impossible. You would be forced to move in the direction of the black hole's rotation simply by existing in that region of distorted space-time. What makes black holes such profound time machines is that their effects are entirely based on well-established physics. Unlike speculative concepts such as wormholes or exotic matter, Black holes definitely exist. We've observed them, measured their effects, and even photographed their event horizons. The time dilation effects near black holes aren't theoretical possibilities. They're inevitable consequences of having such extreme concentrations of mass and energy in relatively small regions of space. The practical challenges of using black holes as time machines are, of course, enormous. The journey to the nearest known black hole would take tens of thousands of years with current technology. The radiation environment near black holes is lethal. The tidal forces, while manageable for supermassive black holes, would still present significant engineering challenges. And perhaps most significantly, these are one-way trips into the future. There's no returning to your own time once you've experienced extreme time dilation near a black hole. Yet black holes remain the most realistic time machines that physics allows. They exist throughout the universe, their time dilation effects are precisely calculable, and the physics underlying these effects has been tested and verified countless times. Every black hole in the universe is a functioning time machine, warping the flow of time according to Einstein's equations, creating regions where the future arrives at dramatically different rates depending on your proximity to these cosmic giants. In the grand theatre of the universe, black holes serve as ultimate demonstrations of time's malleability. They show us that time is not the constant backdrop against which cosmic events unfold, but rather a dynamic part of the cosmic stage itself, stretching, warping, and nearly stopping under the influence of extreme gravity. Near these cosmic time machines, space doesn't just curve, it screams under the tremendous warping effects, while time itself becomes a river flowing at vastly different rates depending on how close you dare to venture to the ultimate point of no return. Every time you glance at your smartphone to check your location, ask for directions to a restaurant, or track your morning run, you're witnessing one of the most remarkable practical applications of Einstein's relativity in everyday life. The global positioning system that guides you through traffic jams and helps you find your way in unfamiliar cities operates in a universe where time flows at different rates depending on your speed and altitude. Without constant corrections for both special and general relativistic effects, the GPS constellation would accumulate errors so rapidly that the entire system would become useless within hours. The GPS system consists of at least 24 satellites orbiting Earth at an altitude of approximately 12,500 miles, traveling at speeds of roughly 8,700 miles per hour. Each satellite carries multiple atomic clocks, some of the most precise timepieces ever created, accurate to within nanoseconds. These satellites continuously broadcast time-stamped signals that your phone receives and uses to calculate your precise position on Earth's surface. The entire system depends on extraordinary timing precision. Errors of even a few nanoseconds translate to positional errors of several feet. Here's where Einstein's universe reveals itself in your daily life. The GPS satellites experience both types of relativistic time dilation simultaneously, and these effects work in opposite directions. Special relativity tells us that the satellite's clocks should run slower than Earth-based clocks because they're moving at high velocity relative to the ground. The effect is small but measurable. The satellite's motion causes their clocks to lose about 7 microseconds per day compared to identical clocks on Earth's surface. But general relativity predicts an even larger effect working in the opposite direction. The satellites orbit in a weaker gravitational field than we experience on Earth's surface, and Einstein's equations tell us that clocks run faster in weaker gravity. This gravitational time dilation effect causes the satellite clocks to gain approximately 45 microseconds per day compared to ground-based clocks. When you combine both effects, the net result is that GPS satellite clocks run about 38 microseconds per day, faster than they would if they remained on Earth. 38 microseconds might sound insignificantly small, but in the world of GPS navigation, it's enormous. Light travels at roughly 300 million meters per second, which means that in 38 microseconds, light travels about 11,400 meters, more than 7 miles. If GPS systems didn't account for relativistic time dilation, your phone would think you were more than 7 miles away from your actual location after just 1 day of operation. After a week without relativistic corrections, the system would be off by more than 50 miles. The error would grow continuously, making GPS navigation completely worthless for any practical purpose. The correction process is fascinating in its precision and complexity. GPS satellites don't simply adjust their clocks and forget about relativistic effects. Instead, the system continuously calculates and compensates for time dilation effects in real time. Ground-based control stations monitor the satellites constantly, comparing their atomic clocks with even more precise atomic clocks on Earth's surface. When relativistic drift is detected, correction signals are transmitted to the satellites to keep their clocks synchronized with the global timing standard. But the corrections go even deeper than simple clock adjustments. The GPS system must also account for the fact that the satellites themselves experience time dilation effects that vary depending on their orbital position. As satellites move through their elliptical orbits, their altitude and velocity change slightly, causing fluctuating time dilation effects. The system calculates these variations continuously and incorporates them into the timing corrections transmitted in the GPS signals. Your smartphone receives signals from multiple GPS satellites simultaneously, typically 4 or more, and uses the precise timing differences between these signals to triangulate your position. Each signal carries not just a timestamp, but also orbital information that allows your phone to calculate exactly where each satellite was when it transmitted its signal. The phone then uses the speed of light to calculate the distance to each satellite based on how long each signal took to arrive. By combining distance measurements from multiple satellites, the system can pinpoint your location to within a few meters. What makes this even more remarkable is that your phone is performing relativistic calculations without you realizing it. Every GPS calculation inherently accounts for the curved space-time around Earth. When your phone determines that you're standing at a specific street corner, it has done so by measuring the travel time of radio signals through curved space-time, automatically compensating for the time dilation effects experienced by satellites orbiting in weaker gravity at high velocity. The GPS system represents perhaps the most widespread practical application of Einstein's theories in human history. Millions of people use GPS navigation every day, and virtually every use depends on relativistic corrections: delivery trucks finding efficient routes, aircraft navigating safely through crowded airspace, emergency services locating people in distress, farmers precisely planting crops, surveyors measuring property boundaries. All of these applications work only because the GPS system continuously compensates for the fact that time flows differently for satellites than it does for users on Earth's surface. The precision required is staggering. GPS timing must be accurate to within about 20 to 30 nanoseconds to maintain the system's advertised accuracy of a few meters. This level of precision means that GPS must account not just for the major relativistic effects, but also for subtle secondary effects, such as the gravitational influence of the Sun and Moon on the satellites, the slight variations in Earth's gravitational field, and even the relativistic effects caused by the satellite's motion through Earth's rotating reference frame. Modern smartphones have made this extraordinary technology so commonplace that we barely think about it. Yet every time you use GPS navigation, you're essentially conducting a real-time experiment in applied relativity. Your phone is measuring how long radio signals take to travel through curved space-time, compensating for time dilation effects, and using Einstein's equations to determine your position in a relativistic universe. The fact that this works seamlessly, delivering accurate results within seconds, represents one of the most impressive technological achievements in human history. The GPS system stands as living proof that Einstein's seemingly abstract theories about the nature of space and time aren't just academic curiosities. They're essential for technologies we use every single day. Without relativity, there would be no GPS. Without GPS, modern navigation, logistics, agriculture, aviation, and countless other fields would be fundamentally different. In a very real sense, we're all navigating through Einstein's curved space-time every time we check our location on our phones, guided by satellites that experience time at a measurably different rate than we do down here on Earth's surface. Time travel to the future, as we've seen, is not just possible, but happens constantly around us. Astronauts return from space having aged less than people on Earth. GPS satellites experience time at different rates. High-speed particles and accelerators live longer than they should because time slows down for them. Forward time travel is established science. verified by countless experiments and essential to technologies we use every day. But travelling backward through time, journeying into the past, presents a fundamentally different challenge that strikes at the heart of logic itself. The classic illustration of this problem is the grandfather paradox, a thought experiment that reveals why backward time travel might be impossible in principle. Imagine you build a time machine and travel back to the 1940s with the intention of preventing a terrible event, say, stopping your grandfather from meeting your grandmother during World War II. If you succeed in this mission, then your father would never be born, which means you would never be born, which means you could never have travelled back in time to stop your grandfather from meeting your grandmother in the first place. But if you never travelled back, then your grandparents would meet normally, you would be born, and you could travel back to stop them from meeting. The loop becomes endless and self-contradictory. This isn't merely a clever puzzle or a plot device for science fiction stories. The grandfather paradox represents a fundamental challenge to the logical consistency of the universe itself. It creates what philosophers and physicists call a causal loop, a sequence of events where effects precede their causes in ways that make it impossible to determine what actually happened. If backward time travel were possible, then cause and effect, the basic logical framework that allows us to understand how events relate to each other, would break down completely. Consider a simpler version of the same problem. Suppose you travel back in time just 1 hour with the sole purpose of preventing your younger self from entering the time machine. If you succeed, then you never travelled back in time, so there's no older you to prevent the younger you from time travelling. So you do travel back in time, so there is an older you to prevent the younger you from time travelling. The paradox doesn't require grandfathers or complex family histories. It arises from any scenario where time travel to the past allows you to interfere with the events that led to your time travel in the first place. Some physicists and philosophers have proposed solutions to these paradoxes, but each solution creates its own problems. The many worlds interpretation suggests that travelling to the past creates alternate timelines or parallel universes. In this scenario, when you prevent your grandfather from meeting your grandmother, you don't erase your own existence. Instead, you create a new timeline where you were never born, while you continue to exist as a visitor from a different timeline. This preserves logical consistency, but at the cost of requiring an infinite proliferation of alternate universes, most of which would be completely inaccessible and undetectable. Another proposed solution is the self-consistency principle, sometimes called the Novikov self-consistency conjecture, after physicist Igor Novikov. This idea suggests that the universe is structured in such a way that any attempt to change the past would automatically fail through a series of coincidences and circumstances that ensure history unfolds exactly as it originally did. Under this principle, if you travelled back to stop your grandfather from meeting your grandmother, something would inevitably go wrong with your plan. You'd miss your flight, get the wrong address, or your interference would ironically be the very thing that brings your grandparents together. The universe would conspire to maintain consistency. But perhaps the most profound possibility is that the universe simply doesn't allow backward time travel to occur in the first place. This isn't a technological limitation. It's not that we haven't figured out how to build a time machine capable of travelling to the past. Instead, it might be that the fundamental laws of physics contain built-in protections against causality violations. Some theorists call this the chronology protection conjecture, the idea that the laws of nature prevent the formation of closed time-like curves, paths through space-time that would allow objects to travel into their own past. Stephen Hawking famously illustrated this concept with his chronology protection conjecture, arguing that quantum effects would become infinitely large near any region where time travel to the past might become possible, destroying any time machine before it could operate. According to this idea, the universe has a built-in immune system against paradoxes. Whenever conditions arise that might permit backward time travel, quantum mechanical effects automatically intervene to prevent it. The evidence from physics supports the idea that nature protects causality. While Einstein's general relativity does allow for theoretical solutions that include closed time-like curves, mathematical descriptions of space-time geometries where time travel to the past would be possible, every realistic scenario for creating such conditions requires exotic forms of matter with properties we've never observed. Wormholes stable enough for time travel would require negative energy densities. Alcubierre warp drives would need negative mass. Time machines based on rotating cylinders would require infinite length and impossible mass distributions. Even more tellingly, every proposed mechanism for backward time travel runs into the same fundamental problem. The energy and exotic matter requirements become more extreme the closer you get to actually achieving time travel capability. It's as if the universe resists attempts to violate causality, making them require increasingly impossible conditions. This suggests that the prohibition against traveling to the past might be more than just a practical limitation. It might be a fundamental feature of reality itself. The deeper we examine the implications of backward time travel, the more we realize that the grandfather paradox is just the tip of the iceberg. Backward time travel would allow for information paradoxes, where knowledge could exist without ever being created. It would permit violation of conservation laws, where energy and matter could be created from nothing by sending them back in time. It would undermine free will by making it possible for future events to determine past decisions. The entire framework of logic and causality that allows us to make sense of the universe would collapse. Perhaps most significantly, the prohibition against traveling to the past protects the universe from becoming logically inconsistent. Forward time travel, which we know is real, preserves causality. Causes still precede effects, even if they do so at different rates for different observers. But backward time travel threatens to make the universe a place where effects could precede their causes, where contradictions could coexist, where the basic principle of non-contradiction that underlies all logical thought would no longer apply. This might be why the universe seems designed to permit forward time travel while preventing backward time travel. Forward time travel allows for fascinating phenomena like time dilation, gravitational effects on time's passage, and the rich complexity we observe in Einstein's universe. But it preserves the logical consistency that makes the universe comprehensible. Backward time travel, by contrast, would create a cosmos where logical contradictions could exist, where cause and effect would lose their meaning, and where the very possibility of understanding reality would disappear. In protecting itself against the grandfather paradox and its countless variations, the universe may be protecting something even more fundamental, the logical structure that makes existence itself coherent and comprehensible. The prohibition against traveling to the past isn't just a curious feature of physics. It's what allows the universe to make sense. Just when we thought we understood time through Einstein's relativity, with its elegant explanations of time dilation, curved space-time, and the cosmic speed limit, quantum mechanics arrives to shatter our intuitions once again. In the quantum realm, the familiar concept of time flowing smoothly from past to future becomes something far stranger and more mysterious. Here, particles can exist in superpositions of different temporal states. Quantum processes can appear to violate causality, and time itself might be built from discrete, indivisible units rather than flowing continuously like a river. The strangeness begins with quantum superposition, the phenomenon that allows particles to exist in multiple states simultaneously until they're observed or measured. We're familiar with spatial superposition. A particle can be in multiple locations at once until measurement forces it to choose a definite position. But quantum mechanics suggests something even more mind-bending. Particles might exist in temporal superposition, occupying multiple moments in time simultaneously until some interaction forces them to collapse into a definite temporal state. Consider the quantum tunneling effect, where particles pass through barriers that should be impenetrable according to classical physics. When physicists measure how long this tunneling takes, they discover something extraordinary. The process appears to happen in zero time, or sometimes even negative time. Particles seem to exit the barrier before they finish entering it, as if they're somehow borrowing time from the future to complete their journey. This isn't a measurement error or experimental artifact. It's a fundamental feature of quantum mechanics that challenges our basic assumptions about the sequential nature of time. Even stranger are quantum mechanical processes that seem to violate the principle that causes must precede effects. In certain quantum experiments, measuring a particle's properties can retroactively determine what state it was in at an earlier time, even if no measurement was made then. The famous delayed choice quantum eraser experiments suggest that decisions made in the present can influence the past behavior of particles, as if information can flow backward through time at the quantum level. This leads us to one of the most profound questions in modern physics. Is time itself quantized? Just as matter and energy come in discrete packets called quanta, time might consist of fundamental, indivisible units rather than flowing continuously. The proposed unit of quantum time is called Planck time, approximately 10 to the negative 43rd seconds, an interval so brief that light can travel only about 10 to the negative 35th meters during its duration. If time truly is quantized, then our perception of smooth, continuous time would be an illusion created by the fact that these quantum time units are far too small for us to detect directly. The implications of quantized time are staggering. It would mean that between any two moments, no matter how close together they seem, there exists a finite number of discrete time intervals. Time wouldn't flow like a smooth river, but would instead proceed in minute, discontinuous jumps, like a cosmic flipbook where each page represents a single quantum of time. Motion through space would actually consist of a series of instantaneous quantum leaps from one position to another, with no actual travel in between. Quantum mechanics also introduces the concept of quantum entanglement, where particles can become correlated in ways that seem to transcend the normal limitations of space and time. When two particles are entangled, measuring one instantly affects the other, regardless of the distance separating them. Einstein famously called this spooky action at a distance, but experiments have repeatedly confirmed that entangled particles really do exhibit these non-local correlations. The effect appears to be instantaneous, suggesting that quantum information can travel faster than light, or perhaps exists outside the normal flow of time altogether. Some interpretations of quantum mechanics go even further, suggesting that time emerges from more fundamental quantum processes rather than being a basic feature of reality. In these models, time is not something that quantum systems exist within. Instead, time is something that quantum systems create through their interactions. The universe might be fundamentally timeless at its deepest level, with the experience of temporal flow emerging only when quantum systems become entangled and create the correlations we interpret as causal sequences. The many worlds interpretation of quantum mechanics adds yet another layer to time's quantum mystery. According to this view, every quantum measurement causes the universe to split into multiple parallel branches, each corresponding to a different possible outcome. Time would then branch continuously, creating an ever-expanding tree of parallel timelines. In this picture, the past doesn't just influence the future. Every moment creates multiple futures simultaneously, and consciousness somehow experiences just one branch of this vast quantum multiverse. Quantum field theory, which combines quantum mechanics with special relativity, reveals even more peculiar aspects of quantum time. In the quantum vacuum, supposedly empty space, particle-antiparticle pairs constantly pop into existence and annihilate each other in time intervals so brief that they can't be directly observed. These virtual particles seem to violate conservation of energy, borrowing energy from the vacuum and paying it back so quickly that the universe's bookkeeping doesn't notice. Time becomes a kind of cosmic credit system, allowing temporary violations of physical laws as long as the books balance in the end. Perhaps most mysteriously, quantum mechanics suggests that the act of observation itself plays a fundamental role in determining the flow of time. The quantum Zeno effect demonstrates that repeated measurements can actually slow down or stop the evolution of quantum systems, as if conscious observation can interfere with time's passage at the quantum level. This raises profound questions about the relationship between consciousness, measurement, and temporal flow that we're only beginning to explore. The intersection of quantum mechanics and relativity creates even stranger possibilities. Some theories suggest that space-time itself might be quantum mechanical in nature, built from discrete units of space and time that fluctuate randomly at the Planck scale. At these incredibly small scales, the smooth space-time of Einstein's relativity might dissolve into a foamy, chaotic quantum structure where the very concepts of distance and duration lose their meaning. These quantum aspects of time force us to reconsider everything we thought we understood about temporal reality. While Einstein's relativity showed us that time is relative and can flow at different rates for different observers, quantum mechanics suggests that time might not flow at all in the way we imagine. Instead, our experience of temporal progression might emerge from the complex interactions of countless quantum systems, each existing in superposition until measurements collapse them into definite states that we interpret as a sequence of moments. The quantum nature of time remains one of the deepest mysteries in physics, touching on fundamental questions about the nature of reality, consciousness, and existence itself. As we probe deeper into the quantum realm, we discover that time's mysteries extend far beyond relativity's elegant equations into a realm where logic itself seems to break down, where cause and effect become intertwined, and where the very notion of when something happens becomes as uncertain as where it happens. In the quantum universe, time doesn't just bend and stretch. It fragments, superimposes, and possibly emerges from something even more fundamental that we don't yet understand. They say space can bend, they say time can stretch, and somewhere deep in the fabric of both, the universe might be hiding a secret passage, a shortcut not just through distance, but through time itself. These are wormholes, silent tunnels in space-time, theoretical bridges that connect one region of the cosmos to another, or perhaps one moment to another. The idea sounds like fiction, like something from an ancient myth or a dream barely remembered. But it's not just dreamers who speak of them. It's the equations of Einstein, the geometry of general relativity. It's the quiet logic of curved space, drawn not in ink but in gravity. A wormhole, at its simplest, is a tunnel between 2 points in space-time. Imagine space as a two-dimensional sheet. Now imagine folding that sheet so 2 distant points touch. A wormhole is the bridge that connects them, not by traveling across the sheet, but by slipping through the fold. In physics, this kind of tunnel is called an Einstein-Rosen bridge, named for Albert Einstein and Nathan Rosen, who first described it in 1935. These bridges emerge from the mathematics of black holes. According to their equations, every black hole might be linked to a mirror twin, a white hole, through a kind of tunnel, a bridge across space, a possible passage between worlds. But wormholes are not roads yet. They are ideas, solutions to equations, mathematical possibilities born from the same theory that gave us black holes, gravitational waves, and the bending of starlight. The problem is, wormholes don't seem stable. The equations suggest they would collapse instantly, closing before anything, not even light, could pass through. They pinch shut like a muscle reflex. The opening appears, but only for a moment, a flicker, a thought, and then it's gone. To keep a wormhole open, physicists say we'd need something strange, something the universe doesn't offer easily. It's called exotic matter, a hypothetical substance with negative energy density. In simple terms, this matter would push instead of pull. It would act like anti-gravity. It could theoretically hold the throat of a wormhole open, keeping the tunnel wide enough for particles, signals, or even travelers to pass through. But no one has ever observed exotic matter. It remains a phantom in the equations, required by theory, but absent in reality. A whisper of possibility. Still, the dream remains. A bridge through space. A shortcut. Through time. If wormholes can exist, and if we could stabilize one, then strange things become possible. Travel to distant galaxies in the blink of an eye. Communication across centuries. Even time travel itself. Because in some versions of the theory, wormholes don't just connect places, they connect times. If one end of a wormhole is moved, accelerated near light speed and brought back, time passes differently for each end. Due to time dilation, one opening might emerge years or centuries after the other. Enter one side, and you step out in the future or the past. A cosmic loop, a portal not just across the stars, but into memory. Of course, there are paradoxes. If wormholes allow time travel, what happens to cause and effect? Could someone prevent their own arrival? Could information loop endlessly without origin? These are not just questions for science fiction. They are questions for physics, and they have no easy answers. Some theories suggest the universe protects itself, that quantum effects would destroy any wormhole the moment it allowed a paradox. Others suggest the timeline simply adjusts, weaving new paths around contradiction. Still others say no wormholes at all, and yet the idea remains unprovable but not forbidden. There's something poetic about that, a theory born from the same field equations that describe black holes and gravitational waves also hints at hidden doors. The math does not guarantee them, but it allows them, like the possibility of dreaming, like the chance of a quiet path through chaos. If wormholes exist, where would they be? Hidden in the void between galaxies? Nested within black holes invisible to us forever? Could the universe itself be laced with such tunnels, microscopic quantum-sized bridges flickering in and out of existence beneath the Planck scale? Some theories in quantum gravity suggest space-time at the smallest scales is not smooth but foamy, a turbulent sea of energy fluctuations and micro-wormholes bubbling in and out. If true, then perhaps wormholes are not rare, but everywhere. Too small to see, too brief to use, but present all the same, a structure beneath the structure. Other models imagine traversable wormholes created by advanced civilizations, engineered with technologies far beyond our own. If an intelligent species mastered negative energy, could they build one? Could they send messages across light years in real time? Could they bend time itself to visit their ancestors or glimpse their distant future? It's not impossible, just unimaginable, to us, for now. And yet, the beauty of science lies in questions that stretch us, questions that don't have easy answers. The idea of wormholes is not about certainty, it's about potential, about the places where theory touches wonder, where mathematics hints at magic, where the cosmos folds quietly in on itself and whispers, there may be more, even if wormholes are never proven, even if they remain. Forever theoretical, they still serve a purpose. They challenge our thinking, they stretch our models, they invite us to imagine reality not as fixed, but as flexible, a fabric, not a wall. They remind us that the universe is not only vast, but complex, that space is not empty, that time is not straight, that distance may be an illusion, and that the shortest path between two stars, or two moments, may not be a line, but a curve. Close your eyes now. Imagine the tunnel, not of steel or stone, but of folded space. Imagine stepping into a room that is not a room, a place where time has no direction, where the stars shimmer outside in frozen stillness, and the bridge stretches on, silent, weightless, indifferent to all that passes through. The walls are not visible, but you feel them curve. Around you, the universe bends gently, and ahead of you, something new unfolds. Not in defiance of physics, but in harmony with it. This is the vision wormholes offer, not a guarantee, not a path yet taken, but a question, a quiet possibility, a thread of thought that connects one moment, here, now, to something far beyond. And maybe that's what we need, not the certainty of a tunnel, but the dream of one. So sleep now, drift slowly, peacefully. The stars do not hurry. The universe does not demand answers, it only offers patterns, and somewhere in those patterns a tunnel may wait, curved, silent, patient, a shortcut not just through space, but through mystery, through wonder, through time. Time travel isn't magic. It isn't a portal hidden behind a bookshelf or a clock that spins backward when the stars align. Time travel, if it is real at all, is built on rules, on physics, on energy and motion, and the strange ways space-time stretches under the right conditions. In this chapter, we leave fantasy behind and walk quietly into the equations. What would it take, really, to journey through time? What tools would a traveller need to bend time not in stories, but in space? The truth is, we've already time-travelled. Every astronaut on the International Space Station returns to Earth a tiny fraction of a second younger than they would have been, thanks to speed. Every person on a mountaintop ages slightly faster than someone at sea level, thanks to gravity. Time dilation is not science fiction. It's science fact. It's already happening. But if you wanted to make it noticeable, to feel it, live it, ride it, the requirements become steep, Not just precise, monumental. Let's begin with motion. According to Einstein's theory of special relativity, the faster you move, the slower your time flows compared to someone at rest. But the effect is tiny until your speed approaches that of light. At 90% the speed of light, time slows down, but not dramatically. You might gain a few extra minutes on Earth while months pass on your ship. At 99% it becomes more noticeable. Time outside your window flows faster. Stars shift, galaxies spin, and you sit in stillness, unhurried by their motion. At 99.9999%, the effect becomes surreal. Travel for just a few years and return to find centuries have passed behind you. This is time travel into the future. Real, measurable, unbreakable. But the price is energy. To reach such speeds, you would need propulsion beyond anything humanity has yet built. Chemical rockets won't work. Even nuclear propulsion struggles. You'd need antimatter engines or fusion drives or something we haven't discovered yet. Something that can accelerate a craft smoothly and sustain it near light speed for years. The energy required increases exponentially as you approach light speed. To reach 90% the speed of light, you'd need roughly half your mass in pure energy. To reach 99.9999%, the requirements verge on impossible. Every step closer to light becomes infinitely more difficult, and no object with mass can ever truly reach it. Light moves alone through that door. Still, if you had the engine, and the patience, and the shielding to survive the journey, time travel into the future becomes not just possible, but guaranteed. Leave at near light speed, return decades later, and find a world that has aged while you remained young. You would not feel the change. Your clock would tick as always. Your body would age normally, but the universe outside would spin forward without you. Speed is one path, gravity is another. According to general relativity, the stronger the gravitational field, the slower time moves. Near a black hole, for instance, time dilation becomes extreme. Get close enough, but not too close, and hours near the event horizon could correspond to years for someone far away. This was famously imagined in Interstellar, but the effect is real. The gravity of a massive object stretches space-time itself, warping the flow of seconds and minutes in measurable ways. But again, the difficulty lies not in the theory, but in the practice. To experience this kind of time dilation, you'd need access to a black hole, and not just any black hole, a large, slowly rotating one whose event horizon doesn't shred you instantly. You'd need a stable orbit close to the edge, deep enough to slow your time but distant enough to survive, and your ship would need shielding against tidal forces, radiation, and gravitational shear, not to mention the energy required to escape afterward. A more subtle tool in the traveler's kit is precision. You don't need to outrun centuries to travel in time. You just need to measure it differently. Atomic clocks placed at different altitudes, or flown around the Earth on planes, tick at different rates. This is time travel at the scale of nanoseconds. But it proves the principle. Time is not absolute. It is shaped, malleable, affected by motion, gravity, and position. And with enough sensitivity, even tiny shifts become meaningful. Now imagine combining these methods. A spacecraft that orbits a black hole at near light speed. The time dilation would be enormous. A few months in that orbit could correspond to millennia elsewhere. When you returned, the world would be transformed, not by choice, but by physics. A journey not through a wormhole, but through waiting, through difference. But what about time travel into the past? That's the dream most people ask about, the longing to undo, to revisit, to warn, to witness. Sadly, the toolkit for that is more theoretical. Special relativity forbids it. General relativity allows it only in special, unstable conditions, wormholes, closed time-like curves, rotating universes, all require exotic matter, negative energy, or impossible configurations. No experiment has confirmed their existence, and many physicists believe the universe simply doesn't allow backwards time travel, that something in quantum mechanics or thermodynamics prevents it, always. But again, the beauty of physics is that it allows questions. Even forbidden paths can be drawn. We can imagine a machine, the Tipler cylinder, an infinitely long rotating mass whose spin bends space-time into loops, or a traversable wormhole where one mouth moves near light speed and returns, creating a time difference between its ends. If you enter the younger mouth, you emerge from the older one. A loop through causality, a doorway into contradiction, and into paradox. If time travel to the past is ever possible, it will not be easy. The toolkit would need components we have never seen, energy types we don't yet know how to generate, materials that bend gravity without collapsing, a perfect understanding of quantum gravity, and safeguards against the collapse of chronology itself. You'd need to thread the needle of the universe and hope the universe allows it. For now, the most realistic time traveler is not someone in a wormhole, but someone moving fast, or falling deep into gravity, or measuring time with exquisite precision. The traveler is an astronaut, a satellite, a beam of light, or even you as you climb a mountain or fly on a plane. You are always traveling through time, but never at the same speed as everyone else. Time is personal, relative, and that's a kind of journey too. The toolkit, then, is not a suitcase. It is knowledge, understanding, equations and clocks and theories that reshape what time means. It is patience, it is curiosity, and above all, it is humility, because time is vast and strange, and it does not bend easily. Close your eyes. Imagine the toolkit not as metal or circuits, but as thought, as geometry, as quiet engines humming in space. Imagine yourself on a ship near a black hole. You glance at your clock. 1 minute. Outside, the stars swirl faster. Civilizations rise and fall in silence. You are still. They are gone. Time is not a river. It is a fabric, and you are learning how to fold it. Sleep now. You've packed your toolkit. The stars are waiting. The seconds stretch, and the future always is in motion. Time is strange. We see it everywhere, in clocks, in stars, in the slow stretch of shadow across a room, and yet we can't touch it. We can't see it directly. What we feel is its motion, not time itself, but its direction. We remember the past, but not the future. We drop a glass, and it shatters, but we never see shards leap back into shape. The sun sets, never rises in reverse. We grow older, never younger. There is a direction to time, a flow, a drift that carries us gently and unstoppably forward. But why? The answer lies not in clocks or calendars, but in something deeper, something older than life. It lies in entropy, the quiet rule that the universe prefers disorder. That over time, things fall apart, not because they must, but because they're more likely to. Entropy is the heart of time's arrow, the reason why yesterday feels different from tomorrow. It's not time itself that moves forward, it's change, and change follows probability. Imagine a tidy room, everything in place. Now shake it gently. Things fall, scatter, shift. It becomes messy. To go from order to disorder is easy. To reverse it perfectly is not just difficult, but nearly impossible. It's not forbidden by physics, but it's statistically unthinkable. There are simply more ways for a room to be messy than clean, more ways for molecules to be jumbled than aligned. Entropy counts those ways, and as it increases, time feels like it moves forward. This is the second law of thermodynamics. In a closed system, entropy never decreases. It can hold steady, it can increase slowly, but it never reverses. And because of this, time appears to have a direction. You can't unmix cream from coffee, you can't unburn wood into trees, and you can't return to yesterday, even if all the particles are still here, because their arrangement, their order, has changed, and with it, time has flowed on. But physics itself doesn't care about direction. The laws that govern motion, gravity, even quantum mechanics, they work just as well in reverse. A planet orbiting backward obeys the same rules. A bouncing ball, reversed in time, is still a solution. So where does the arrow come from? If the rules are symmetrical, why isn't time? The answer is in the initial conditions. The universe, at its birth was extraordinarily ordered, smooth, uniform, low in entropy. It had structure, not in stars or galaxies, but in simplicity, a kind of cosmic neatness. From that moment, entropy began to rise. Gravity pulled matter into clumps. Stars lit, planets formed, life emerged, all of it increasing the complexity, and with it the entropy, of the universe. Every moment since that beginning has followed a path of increasing disorder. And so, memory is built in one direction. We remember what was, not what will be, because the past was more ordered. And the brain, like everything else, is a physical system, shaped by entropy. You cannot store a future that hasn't happened, but you can recall a past that left its mark. This is why time feels like a river flowing downstream, not because the river has intention, but because gravity pulls water one way. In the same way, entropy pulls time. It gives events a slope, a tendency, a preference for forward. Even the idea of cause and effect comes from this. You light a candle, and flame appears. You speak, and a sound follows. But if time reversed, those chains would break. Flames wouldn't cause light. Voices wouldn't echo. The relationship between events relies on direction, and that direction emerges from entropy's climb. But what if entropy could be reversed? What if a region of space became more ordered over time? In theory, it could happen, but the odds are so low, so cosmically small that we'd never see it. To reverse entropy is not impossible, just unbelievably unlikely. It would require every particle in a system to move in exactly the right way. And the universe simply doesn't work that way. It doesn't forbid the impossible, it just forgets it. Still, in physics, strange things happen. At quantum scales, time behaves differently. Particles flicker, entangle, shift in unpredictable ways. Some interpretations even suggest that time is not fundamental, that it emerges from deeper laws we don't yet understand. But entropy still reigns. Even in the quantum world, it rises. It hums beneath reality like a soft drumbeat, always pointing forward. And so we live in a world where eggs break but do not unbreak, where ashes do not become logs, where we wake each morning a little older, not because something pulls us forward, but because entropy does not let us return. This is the quiet truth of time's arrow. It's not painted on the stars, it's not built into the ticking of clocks. It's in the way energy spreads, the way heat moves, the way systems tend toward disorder. You feel it in your body, in memory, in the way breath comes and goes but does not linger. Time moves forward because the universe cannot and will not remember what it hasn't yet become. Close your eyes now. Picture a droplet of ink falling into a glass of still water. At first it is whole, contained. Then it blooms. It spreads, curling gently into whirls and threads. You watch it dissolve. You cannot undo it. You cannot gather it back into that perfect droplet. It was simple. Now it is complex. It was still. Now it is motion. This is time's arrow, made visible in a glass. You carry this arrow in your cells, in your thoughts, in the way you remember beginnings and imagine endings, in the fact that you know your past, but not your future. That is not a failure of knowledge. It is the shape of time itself. Perhaps someday we'll understand entropy at deeper levels. Perhaps time will reveal more of itself. But for now, we walk forward, gently, on the slope it provides. We live inside its direction, and we make peace with the fact that every moment is new, not because the future is promised, but because the past cannot return. Sleep now. The world will continue to warm, to unfold, to stretch gently toward disorder, not with violence, but with patience, with soft complexity, with the quiet pull of thermodynamics. You do not need to race time. You only need to rest within it. Let it carry you like a river, not backward, not forward, but through. And somewhere, beyond understanding, entropy will whisper its next line, and the universe will listen. You live in Einstein's universe, even if you've never noticed. You don't need to ride a spaceship or orbit a black hole to feel its effects. You feel them every time you check your phone, every time your GPS locates you on a map, every time an atomic clock ticks deep in the heart of a satellite. You may never see space-time curve with your eyes, but its gentle warping shapes the world around you, quietly, precisely, always. When Einstein reshaped physics with his theories of relativity, he didn't just describe how fast things move or how gravity works. He changed how we understand time itself. He showed that time is not constant, not universal. It is elastic. It flows differently for different observers. And this isn't just theory, it's reality. Time dilation, the slowing or speeding up of time based on speed or gravity, isn't something that only happens to astronauts and particles. It happens to you every day. Let's begin with satellites, those quiet machines orbiting high above Earth. They don't just beam signals, they keep time, atomic time, the kind of time that measures nanoseconds with breathtaking precision. These clocks are the beating hearts of GPS systems. When your phone calculates your location, it doesn't use maps. It uses time. Signals from at least 4 satellites are compared. Each one carries a precise timestamp. The time it takes those signals to reach you tells your device where you are. But here's the trick. Time on those satellites flows differently than it does down here. Because they're moving fast and orbiting far from Earth's gravity, their clocks tick slightly faster than clocks on the ground. Special relativity says speed slows time. General relativity says gravity slows it too. But in this case, the satellites are farther from Earth's gravity well, and that makes them tick faster. The combined effect is about 38 microseconds per day. Tiny, but enough to throw GPS off by kilometers if uncorrected. So we correct it. Constantly. We adjust our devices to account for the stretching and squeezing of time, all because Einstein said we must. And it's not just GPS. Particle accelerators, like those at CERN, push particles close to the speed of light. As they race around the accelerator ring, time slows for them. This is not hypothetical. It's observed. Particles that decay in microseconds suddenly live longer, because they are moving so fast their internal clocks tick more slowly. This time, dilation is real, measurable, repeatable. We've built machines that count the seconds inside Einstein's theory, and found that his equations keep perfect rhythm. Even cosmic rays, high-energy particles from space, teach us this truth. Some of them, like muons, should decay before they reach the surface of Earth. Their lifespan is short, too short to make the journey. And yet they do, not because they live longer, but because their time has slowed. From our perspective, they survive the fall. From theirs, the distance shrinks. This is relativity in motion. And it happens above your head all the time. You don't need a lab to feel this. Hike a mountain. Sit in an airplane. Climb a few flights of stairs. Each time you rise higher, you move ever so slightly away from Earth's center. The gravity weakens, and your time flows a little faster. Not enough to notice, not enough to change your day, but enough to be real, enough to measure. If you had 2 perfect atomic clocks, one on a mountaintop, one at sea level, they would drift apart. One ticking slightly ahead, one lagging just behind. The difference is small, but it accumulates. Even in your body, relativity whispers. Your feet slightly closer to the Earth's center than your head. Experience slightly stronger gravity. Time flows differently between your toes and your crown. You are a vertical gradient of time, a slow cascade of seconds from head to heel. Not enough to matter in daily life, but enough to remind us the universe is curved, not flat. Time is shaped, not fixed. So what does it mean to live in Einstein's universe? It means understanding that time is personal, that your experience of a moment is not universal. 2 observers moving differently or sitting in different gravitational fields will disagree about what now means. And yet, each is right, each is valid. Time has no master clock, no singular beat. It is woven from the fabric of motion and mass, and that fabric ripples everywhere. It means that even though we feel time is steady, a metronome ticking forward, it is anything but. It bends, it shifts, it stretches in the presence of mass and speed. And we have built our world around those shifts. Our phones, our planes, our satellites, our science, all shaped by the fact that time is not absolute. This may seem abstract, but it is deeply human. It tells us that perspective matters, that what you experience is not the only truth. It also reminds us that the universe is not built on simplicity. It is built on subtlety, on nuance, on the quiet grace of warped coordinates and local truths. And still, amid all this complexity, there is harmony. The equations still work, the clocks still tick, the GPS still guides, the sky still holds its stars. Close your eyes now. Picture a web stretched across space, each point a clock, each strand a path through time. Some strands dip under gravity, others stretch under motion, but the web holds. It flexes, it breathes, and you are somewhere inside it, suspended in a rhythm that is yours alone. You are living in Einstein's dream, a world where time dances softly with gravity, where motion is not just movement, but a change in tempo, where every second is local and every clock tells its own story. You may never feel the dilation, but it is there, shaping your breath, your step, your place in the cosmos. This is not science fiction. This is now. You don't need a time machine to travel through Einstein's universe. You are already in it, moving, aging, measuring, living. And with each quiet second, the curve of space-time enfolds you. Sleep now. Let the seconds stretch. Let gravity rock you. Let time, not rigid but gentle, carry you forward in its soft, curved cradle. The stars move slowly overhead. The satellites drift with precision, and your clock, like all clocks, ticks within the rhythm of relativity. You are exactly where you should be, in motion, in stillness, in time. You're already drifting through time. Every second that passes, every breath that fades into the quiet air carries you forward. You don't need a machine. You don't need a wormhole. Time travel has already begun, not as fantasy, but as fact. And yet, we imagine more. We wonder, could we shape this motion? Could we direct it? Could we stretch it so far that we slip past stars and decades and wake in a new world, barely older, while history has flowed behind us like a river? This is the dream of the time traveler, not one of paradoxes and loops, but of gentle patience and profound distance, a dream not of rewinding the past, but of stepping into the deep future. And in the quiet heart of Einstein's equations, it may already be possible. Imagine a ship, not a silver blur or a spinning portal, but a generation vessel, vast and humming, built for a journey that will outlast lifetimes. It accelerates slowly, steadily, pressing ever closer to the speed of light. As it approaches that ultimate limit, time inside slows. Days pass on board, while years pass beyond its hull. The crew sleeps, wakes, grows, but barely ages. Their clocks tick slowly, their atoms hum at a gentler rhythm, and outside civilizations rise, fall, and forget. The ship sails not just through space, but through time. This is not fantasy, it is time dilation. The same phenomenon we see in satellites and particle beams, scaled up to starship size. The faster you move, the more time stretches. If you could ride that dilation long enough, you could reach distant stars and return to find Earth transformed. Generations gone, landscapes changed. You would have travelled not just far, but forward. Of course, the challenge is immense. To reach such speeds would require vast energy, propulsion systems beyond our current engineering, and shielding against cosmic radiation. But the physics does not say no. It only says, not yet. And perhaps one day, this slow-motion leap across time will be humanity's first step into interstellar life. But what would that mean? To live outside time? To age differently than the rest of the species? Would you feel dislocated or deeply free? The philosophy of time travel is as profound as the physics, because time is not just a number, it is how we measure existence, relationships, loss, memory. A traveller who skips centuries might arrive in a world where language has changed, where nations have vanished, where no one remembers the earth they left. It is not just a physical displacement, it is an emotional one. And yet, In that dislocation is a gift, a glimpse of time as it really is, not fixed, not equal, not absolute. To travel through time is to see its texture, its flow, its malleability. It's to experience what Einstein showed, that time depends on where you are and how you move, that seconds are not universal, that clocks do not all agree, and that reality itself is drawn on a flexible canvas. Maybe one day we'll do more than travel forward. Maybe we'll master exotic matter, stabilize wormholes, bend space-time like an artist bends light. If that day comes, we may walk not only into the future, but into the past, not as tourists, not as conquerors, but as careful dreamers, moving through moments with reverence. Until then, we listen, we learn, we build our clocks and spacecraft and theories. We measure time as best we can, even as it quietly resists definition. Because time, in the end, is more than something we watch tick away. It is the stage on which everything plays out. The silence between stars, the rhythm in our cells, the gentle drift from birth to becoming. And tonight, as we close this journey together, that realization settles softly that you exist in Einstein's universe. Not a simple universe, not a clockwork cosmos, but a curved, breathing world where space flexes and time bends, where gravity isn't just a pull, it's a ripple, where light has no mass but carries memory, and where you, floating in the present, are part of something immeasurably large and yet intimate. Time is not just what your watch tells you. It is not just a direction. It is a dimension, a medium, a mystery that wraps itself around everything you know. And though you cannot hold it, you can move through it. You already are, 1 second at a time. So imagine now the future. A child is born on Earth. Another is born aboard a ship bound for Alpha Centauri. Decades pass. On Earth, that child becomes a grandparent. On the ship, the traveller is still young. When the ship returns, the two meet, one weathered by years, the other barely changed. And in that reunion is proof. Time is not the same for all. This is not science fiction. It is science. It is happening now, on smaller scales. And it points to what's possible, a quiet, profound reshaping of our place in the cosmos. Perhaps, as technology evolves, we will live longer not by changing biology, but by changing time. Perhaps we will escape catastrophe by skipping centuries. Perhaps messages will be sent forward, not through wires, but through flight. Perhaps one day, the stars will not just be distant, but reachable through the bending of hours and days. But even if we never build that ship, never hold open that wormhole, you are still a traveller. You are still in motion. The Earth spins, the galaxy turns, the universe expands, and time flows, not like a river, but like a breath, elastic, invisible, essential. As you drift towards sleep tonight, let that knowledge rest with you. That time travel isn't just a dream, it's the universe you live in. That when you age more slowly at altitude, when a clock in orbit ticks differently than one on the ground, that's time bending, not breaking. That when you look at a star, you are looking into the past. And that even now as you breathe, you are stretching the seconds gently across space. The traveller's dream is not about leaping centuries or rewriting history. It is about understanding, feeling, realizing that we are not trapped in time. We are shaped by it. That time is not the enemy. It is the vessel. And perhaps, in this quiet moment, you feel that, not as noise, not as urgency, but as peace, as stillness moving. Close your eyes now. Let the clock fade. Let the ticking dissolve. Let the stars come close. You are not waiting for the future. You are already in it. You are not chasing time. You are held by it. And as you float in that thought, the final truth settles gently. Time isn't something far away. It isn't a gate or a machine. It is the soft curve beneath everything, the canvas on which reality is painted. And you are already part of the masterpiece. Sleep now, traveller. The journey has already begun.